A warm welcome to all the viewers for the course Strength of Materials. Myself Thiapal, Assistant Professor of Department of Mechanical Engineering, JI's College of Engineering, is going to deliver a lecture on today's topic, that is torsion, or you can say torsion on a circular shaft. So, if you look at this workshop or industry, then you might have seen that a turning force has been implemented over the rotating body to transmit the energy. And so, if I talk about this particular thing, then mainly I can say this turning force or the twisting moment, it basically implemented over the rim of the wheel, or even if I tell about the key that is associated with the shaft, or in fact you can consider a point in an object which is at a distance that is really apart from the axis of the particular shaft. Okay. So, if I talk about this torsion, turning force is always applied to the rotating portion to transmit the energy. So, the product of this turning force and distance of the application of the force and the axis of the shaft, it is known as torque. So, basically what is torque? I can say that it is the product of the turning force into the portion where you are implementing the force, which is at a distance which is apart from the point of application and you can say the axis of the shaft. So, this is known as the torque. And finally, the shaft is said to be subjected to torsion. And the most important thing is that due to this torque, any of the section of that particular shaft, they basically feel or they are subjected to some sort of shear stresses. So, today in this particular lecture, which is already in your course and in the module of 5, which we are having torsion on circular shaft, this will be the first introductory lecture of torsion. So, without any further delay, now let us move to the next slide, where we are going to have a look at the content. So, in the content, what we are going to have initially, that we will be talking about all about the introduction of this particular torsion, what are the assumptions that we should consider for this particular topic. Let us have a look here. So, introduction, we are considering that you can see this is particularly a circular shaft. This is particularly a circular shaft and you are giving some sort of turning moment. So, you just consider a what I will say, just a circular premistic bar, and it has been subjected to some sort of moment, that is moment along mx direction, moment along my direction and mz direction as it has shown in the figure. So, you can see this is your x direction, this is your x direction and this is your y direction and this is your z direction. So, in this particular shaft you are able to see that some sort of moment has been provided here. So, in the above case, moment mx and my. So, you can see this is your mx, this is your mx and this is your my. They causes rotation about the transverse axis. So, this is your transverse axis and this is your transverse axis. So, in this particular condition, you can see that this particular shaft is there and you are providing a moment along mx direction, along my direction and along mz direction. And here you can feel that the moment that is caused due to rotation about the transverse axis, and hence mx and my are the bending moment. But if I consider the mz, in case of mz, this causes rotation about the longitudinal axis, or which is also known as polar axis. So, you can see this is the longitudinal axis which is also known as polar axis, and here at this particular moment is occurring, that is the mz, due to the cause of rotation about your longitudinal axis or polar axis. So mz is also called torsional moment, or it is known as twisting moment. So from this figure, if you just have a look, then you can see it that here we have got three different moment: mx, my and mz. In case of mx and my, the moment is occurring due to some cause of rotation but about your transverse axis. But mz is such sort of moment that is there which is caused due to the rotation but about your longitudinal axis, or it is about polar axis. And so mz is also known as torsional moment or twisting moment. So torsional moment and twisting moment both are basically same. So in this particular slide we can see that we are having the torsional moment also as well as twisting moment also. Along which axis? Along the longitudinal axis or polar axis, because the bending is caused due to the rotation about the bending about the longitudinal or polar axis. So if you think in the field of solid mechanics, then I must say torsion is the twisting of an object due to applied of torque. So torsion is basically expressed in Pascal, and you can see SI unit for Newton per square meter. So Pascal, as you can see, but if I have a look for the thing in the SI unit, then I must say that you are getting as Newton per square meter, or in pound also pound per square inch, which is PSI. But while torque is expressed in Newton meter or foot pound forces in some of the cases, but in sections that is perpendicular to the torque axis, the resultant shear stress is in this section which is perpendicular to the radius. Next thing what we are going to that, if I consider a circular cross section, then basically the twisting is accompanied by a distortion which is also called wrapping, and in which the transverse section do not remain plane. And for shaft of uniform cross section which is unrestrained against wrapping, then the torsion equation is basically said by capital T is equal to J by R into tau, or you can say J T by L into G theta. So these are the things that we need to know about the torsion. So again I am repeating that if I talk about or if I say in the field of solid mechanics, then torsion is the twisting of an object due to the applied of torque, and basically it is expressed in Pascal, and if I go with the SI unit, then it is Newton per square meter. Okay. Now T what we have told for the equation, then T is none other than the applied torque or the moment of torsion, which is always represented in Newton meter. And if I talk about the tau, that is the maximum shear stress at the outer surface, because I have already told due to this turning force or due to this torque, the object is wherever we are applying this particular load or the twisting force or the turning force, due to this torque, that particular object plane is basically getting or experiencing some shear stress also. That's why tau in this particular equation, it is represented by maximum shear stress at your outer surface. Now Jt that I have told, it is nothing but that is your torsion constant, and for the section you are considering, and if you are using some sort of circular rod and tube, then with a constant wall thickness is also there, and it is equal to the polar moment of inertia of the section. But for outer shapes or split section, it can be much less also, and for more accuracy finite element analysis, that FEE is the best method to calculate the thing. Another calculation method can be included to calculate the torsional constant, and that includes the membrane analogy and shear flow approximate also. Now, if I consider small r, that is, what is this r? It is nothing but the perpendicular distance between the axis, rotational axis, and the farthest point of the section, that is at the outer surface. Again I am repeating, you are considering some sort of r, which is none other than the perpendicular distance between your rotational axis and also the farthest point in the section, which is also known as your outer surface. Now you are considering as L, which is your length of the object to or over which the torque is being applied. So L is what? Your length of the object to or over which your torque is being applied. And if I talk about the phi, it is none other than the angle of twist in radian. In some sort of experiment you can see, you can get theta. Theta is also the angle of twist. So phi also you can use theta. Any book if you follow or any lecture note if you follow, then there are various various symbol they are representing the angle of twist, and it is always represented with theta or phi, and the unit has been considered as radian. Now I will be talking about G. Somewhere in the equation you might be getting G, or somewhere you might be getting capital C. It is none other than your shear modulus. Okay, shear modulus, which is also called the modulus of rigidity, that I have already explained what is modulus of rigidity in my first module lecture. So we need to get in details about the modulus of rigidity, or you can term that as shear modulus. But the most important thing is that it is basically given as gigapascal, or in fact in megapascal, anything it can be. But if I go with the ISO unit, then it is always Newton per millimeter square. So again I am repeating the formula for the torsional equation for a shaft with a uniform cross section. If I tell for the unrestrained against wrapping, then the torsion equation is always represented by your capital T, and that is none other than the torque or the moment of torsion, and the equation it is represented by J suffix T by R into tau. Tau is your maximum shear stress, or you can write as G theta J T by L, that is your length, into your G theta or G phi. So theta or phi, whatever may be, it is none other than your angle of twist, which has been represented by your what? It is represented by your radian. So hope from the introduction you are able to know that what I am actually meaning to say about the thing in this particular introduction. So now let's move to the next slide. Now as we are aware of so many terms, that is bending moment and twisting moment. But what is bending moment or what is twisting moment, or in fact what is the basic difference between bending moment and twisting moment, that we are going to study right now in this particular slide. So if I talk about the bending moment, then the first thing that I would like to say is that in bending moment, in bending, I must say, moment or couple act always about your transverse axis, or you can say transverse axis. So transverse axis, as I have already told you, that we are considering it as X or Y, and we are considering as the polar axis or your longitudinal axis as always your Z. So bending moment, when we are discussing always, then we can say that we are following the moment or the bending which is occurring, or I must say the bending, that in case of in bending moment or couple always act on the transverse axis, that is your XX or Y by axis. Next we are talking about the bending moment. So in bending, the plane of cross section rotates about your neutral axis. So again I am talking about neutral axis. So in bending, again I am repeating, the plane of cross section which basically rotates about your neutral axis. And finally, what I am telling, it is that is due to bending, the normal stresses are produced which vary from 0 at neutral axis, and you can obtain maximum at the top and the bottom surface, that is your extreme fibers. So again I am repeating, if I talk about the bending moment, then I must say in bending basically moment or couples both act about the transverse axis or transverse axis, which you can consider as to be XX direction or YY direction. But again one more thing you have to keep in mind, that is bending. In case of bending, the plane of cross sectional always rotate about your neutral axis. And finally what we are talking here right now, that is due to this bending, the normal stresses that are produced which basically varies from 0, and this 0 value is obtained none other than in your neutral axis, and you can obtain the maximum value for normal stresses in your outer surface or at the top surface or bottom surface of that particular product. That means that is the extreme fiber portion of that particular product or the circular shaft. There you can obtain your maximum normal stresses, but you have to remember in case of bending, your the main value for your normal stress is 0 at your neutral axis. Now we have came to know about your bending moment. So now we will be having a look for, that is your twisting moment. So what we think about the twisting moment? So let's have a look here. As you can see, for twisting moment, you can see that is in twisting, couple act along the longitudinal axis or polar axis, which is along ZZ. So twisting moment is also known as your turning moment, that I have already mentioned in the introduction portion. So there you can see is that bending moment is always occurring along your x axis, y axis, that is along your transverse axis, but the twisting moment, it is acting along your longitudinal axis, or you can say the polar axis, that is your ZZ direction. Second point it has been told, that is in twisting, the plane of cross section always rotate about your polar axis. Hence the radius or the radial rotate about your polar axis also. So if you are thinking that is the plane of the cross section, in twisting if you consider the plane of the cross section, then it basically rotates about your polar axis. So you know that we are having a polar axis and it is rotating about, the plane is rotating about the polar axis. So if the plane is rotating about the polar axis, then obviously the radii will be also rotating about the polar axis, because you are considering a circular shaft. So twisting is occurring, basically your twisting is occurring when your plane of cross section actually rotates about your polar axis or your longitudinal axis. But if I talk about the bending moment, then again I must say that in case of bending, the plane of the cross section always rotate about the neutral axis, which is always denoted by NA. So NA is none other than, here maybe some people are getting confused, let me write it, that is NA is none other than, it is neutral axis. So you can see here that NA is none other than your neutral axis. And finally, if I talk about the twisting moment, then I must say that is due to this twisting, only shear stress are produced, which actually, which actually acts in two mutually perpendicular plane, and it vary from 0 at polar axis to maximum at the surface in the circumferential direction. So circumferential direction, you know that you are having as the outer direction, and this basically twisting moment is occurring, and due to this twisting what is actually happening, it is only a shear stress, as I have already told that due to this twisting only the object is facing, or you can say the object is experiencing some sort of shear stress. So due to this twisting only shear stress are produced, which are basically act in two mutually perpendicular plane, and it varies from 0 at polar axis to maximum at the surface in the circumferential direction. So what I was telling again, if I come to summarize this particular slide, and we are aware of what is bending moment and what is the twisting moment, then the most basic difference that we are getting, that is about the axis of the rotation that are occurring, then the plane of the cross section through which they are getting rotated, and next we are calculating that where we are going to obtain the maximum stress, that is for bending moment we are getting the normal stress, and for twisting moment you are getting the shear stress. So where we are going to get the maximum stress in both the cases, that is the basic difference. So the basic difference are varied with respect to these three parameters that I have discussed right now. So if I come to the conclusion of this particular difference between the bending moment and the twisting moment, then I must say again that is in case of bending moment or couple basically act about your transverse axis which is along the x-axis and y-y direction. In case of twisting moment, obviously I mean to say the couple act along the longitudinal axis, or even you can say polar axis, which is along your zz direction. And in case of the bending moment, basically the plane of cross section rotates about your neutral axis. But if I talk about the twisting moment, then I must say the plane of cross section always rotate about the polar axis. So hence the radial of the rotation is also occurring about the polar axis too. And finally, if I talk about the bending moment, then I must say that normal stress you can obtain from 0 to maximum, that is from, if you are obtaining 0 value, that means it is towards the neutral axis, or even you can say at the neutral axis, and you can obtain maximum normal stress value at the top or at the bottom of the surface, that is your extreme fiber. But if I talk about the twisting moment, then I must say that due to this twisting only shear stresses are produced which act into mutually perpendicular plane and vary from 0 at the polar axis to maximum at the surface of the circumferential distance also. So now let's have a look for the next slide. So whenever we are talking about the torsion, that means there is some theory or behind this pure torsion. So what are the assumptions that we should follow or that is involved in the theory of pure torsion, that we are going to have a look right now. So first thing what I am getting, it is none other than, that is, material is isotropic, it has to be homogeneous and linear elastic, in which Hooke's law is valid. So again the term Hooke's law is coming. So Hooke's law is what? Where stress is proportional to the strain, and that should be within elastic limit. So there is no confusion to consider. This is one of the assumptions that is involved in the theory of pure torsion, that is, material is isotropic, it should be homogeneous, and it should be linear elastic, in which the Hooke's law is also valid. Now let's move to the second assumption, that is, the shaft should be perfectly straight and uniform in cross section. So you cannot use any sort of bending shaft, or you cannot use some sort of distortion shaft. It should be perfectly straight. Not only straight, the cross sectional area, it has to be uniform. Next we are talking, that is, torque that has been applied to the shaft, it should be all about the axis of the shaft. So when you are considering a shaft, there is axis of that particular shaft, isn't it? So the torque has to be applied on the shaft and it is about the axis of the shaft. So this is also another consideration. So you can see this is the figure, you can see, and there what I have told you, that is if you consider this is your longitudinal axis, this direction, this is your longitudinal axis. If I consider it by another line, red line, then you can understand this is your longitudinal axis, or it is known as the polar axis. And what I was talking about the transverse axis, then I must say this direction, it is your transverse axis. If you consider this as your transverse axis, this is along your x-axis direction. Another transverse axis you can consider, that is this one. Okay, this is also your another transverse axis. So this is your y. So again I must say this is your x, this is your x axis, and this is your y axis, this is your y axis, and this is your z axis, this is your z axis. So from this particular figure you are able to know that what is basically the axis that is occurring. So whenever you are talking about the torque, it is always applied to the shaft. It is torque, when we are talking, then we must say torque is always applied on the shaft, and that is about the axis of the shaft. So whenever we are talking about the axis of the shaft, so you can see this is your axis of the shaft, and this is also known as your longitudinal axis, or it is also known as your polar axis. Now we are coming for the fourth assumption. So in this fourth assumption, what has been told, you just have a look here. That is the plane section. The plane section, you can see this, that is, this is your plane section. Okay, this circular is your plane section. Should, before twisting, okay, before twisting and after twisting, it should remain plane. Is that clear? I mean to say the plane section before twisting should remain plane after twisting also. So though it is your object, you are giving some turning force, that means you are making it a twisting or turning moment you are arising in this particular shaft. So in this particular section, the another assumption that you have to consider, that is the plane section before twisting remain plane after twisting also. It means that the radii which are straight before twisting will remain straight after twisting also. So right now you are considering the radius as OA before twisting. So initially this OA is the radius in the circular plane of the circular shaft, and before twisting the radii has to be considered as OA. So when you are making a twisting, that means from O you have reached to OA position, OA dash position. So that will also remain same, the radius of the twisting will also remain same, that is equal to your R. So what I was telling, that you have to remember it, that OA is what? That is your radius before twisting, and OA dash, it is the radius after twisting, and that has been represented equally to as R, that is the radii of the particular circular shaft. So according to one of the assumption that has been involved in the theory of your pure torsion, that is the plane section, that is before twisting remain plane after twisting also. That's why we are able to write this particular theory. Okay. And finally we are coming to the last assumption, that is for pure torsion. If you consider a pure torsion, then area of the cross section should be circular and prismatic, and it can be solid also or it can be hollow also. So if you want to have a torsion theory for any sort of circular shaft, then one of the finest assumption that you have to consider, or that is involved in the theory of pure torsion, that is that area of the cross section should be circular and prismatic, and it may be solid also or it can be hollow also. Again I am repeating, for pure torsion the area of cross section should be circular and prismatic, and it may be solid also or it may be hollow also. So now we are going to have a look for the sign convention. As you know, we have to consider when we are going to be considering it as positive or when we will be considering it negative. So in this particular figure, if you go for this one, you can see this is a shaft and you are giving a clockwise movement. Okay, clockwise turning force you are applying. So you can see this has been considered as straight, this torque that is been considered to be as positive. So that means if it is in this particular direction, that is TA is equal to T, and this T is your positive. But if you consider, you see this was in clockwise direction, you can see this was in a clockwise direction. So your value for your torque is positive, but right now this is your anti-clockwise direction. So for this particular condition, what you are seeing, the torque, it is in the outward direction. So you have to consider it as torque negative. So positive when it is inward direction, and this torque sign convention will be negative when it will be in the outward direction. So as per the sign convention, you have to follow some rule, that is the sign convention can be explained with the help of your right hand thumb rule. If the torque is applied in the direction of the right hand figure, then the moment of the nut due to the torque will be in the direction of the right hand thumb, and if the right hand thumb pointed towards the cross section, then the torque is treated as positive at the section. And you know, a positive torque will produce a positive shear stress element on the surface and vice versa. So positive torque will produce positive shear stress, that means negative torque will also produce negative shear stress element on that particular surface. So you have to remember this sign convention also. Now what are the effect of torsion? So if I talk about the effect of torsion, then I must say, due to this torque, shear stress are developed in two mutual perpendicular plane. One in the plane of cross section in the circumferential direction, another normal to the plane of cross section in longitudinal direction. So what are the thing? That is, one is circumferential direction you are considering, another you are considering at the longitudinal direction. So this thing you have to remember, that what are the various effect of torsion actually there is. Now we are talking about some torsional stresses and strain. So you can see this has been considered to be as a circular shaft, and you know L is the length, theta is there, that is through which you are rotating this one. Phi is also there, this is the angle of twist, and this is the turning force you are implementing, or the torsional moment you can say. This is G, it can be represented by G also or C also, that is modulus of rigidity. Again you can see what are the consideration that I have taken. T is your torque, again remember T is your torque, L is the length of the shaft which has been considered in millimeter, and R is the radius of the circular shaft. So torsional stress strain, what we are considering, again that angle ACA that has been represented by phi in degree, okay, and you are considering angle AOE that has been represented as theta, that has been radian, and tau you know that is your shear stress that has been induced in the surface, and G, or you can C you have written, you can also write it here as G also, okay, this can be written as G also, it does not matter, G, it can be written as C or it can be written as G, it does not matter, because it is all about the modulus of rigidity along your torsional or it is known as the torsional rigidity of that particular circular shaft. So according to the shear strain, we know A dash is by L, it is represented by tan theta, and this tan theta is also termed as tan phi. Why? Because the phi is very small. So tan phi can be written as phi also. And also we know that arc, that is A dash, it is represented by r theta. So if I tell phi, this phi is none other than A dash by L. So A dash can be also written as r theta. So this is the first equation that you have received. That is phi is written as r theta by L. This is the first equation you have obtained. Now second thing what you are getting, it is all about that if tau is your intensity of shear stress on the outermost layer and C is the modulus of rigidity of the shaft, then phi can be represented by tau by C. So this is your second equation. Next what you are getting from this equation 1 and 2, if you solve, then what you are getting, tau by C is equal to r theta by L, or you can write tau by r, it is also known as c theta by L, or you can say tau by r is equal to g theta by L. So if you want to have the shear stress at the x direction, that is the intensity of the shear stress on any layer at a distance of x from the center of the shaft, then I must say that is tau x is none other than tau x by x, which is also represented by tau r is equal to g theta by L. So if I talk about the strength of a solid shaft, you can see that this is particularly a circular section of the shaft you have achieved, and there what you are getting is that we are considering a certain point, that has been O has been considered here, and at a distance of x you have taken a strip, and r is the what radius that you have considered of the shaft, and tau is the shear stress. So if I talk about the elementary strip area, that is dA, that is none other than what is 2 into pi into x into dx, and tau is your maximum shear stress. From there what you are getting, that is turning force is always known as shear stress into area, and finally what you are getting, that is 2 pi tau into x square into dx by r. Now if you further go on deriving this one, that is you need to know for the turning moment, then turning force into the distance of the element from the axis of the shaft, and you have got the value as 2 pi tau by r into x cube into dx. And further if you integrate, because your inner portion is what, at 0, and outer is maximum radius that has been considered as r. So if you want to obtain the total torque that has been induced in this particular shaft, then you have to integrate it. So further in integrating this turning moment, what you are getting, that is pi by 16 into tau into dq. This is your total torque that has been considered in this particular program. So here you can see a numerical. For example, the same thing has been told. You have to find out the minimum diameter of this shaft, and for this what you need to know this one. So torque has been given here to you, and the maximum shear stress has been also provided to you. So the data is known to you. So what you know, that is T is equal to pi by 16 tau into dq. So you know the value of your torque, you know the value of stress, you don't know only the value of diameter. So by putting this one, you are able to calculate the value of your diameter, as you can see. So now we are concluding my lecture for part 1 in torsion, or you can say torsion in a circular shaft. I would like to request you to follow the video lecture, so that in my next lecture we can discuss about the various things that are associated with solid shaft as well as for hollow shaft. Also we are going to discuss about the shear stress that has been induced in this particular shaft, and so and so. So if you have liked the video, then stay connected with me, subscribe my channel, and please like and share my channel. So again I am repeating that today we have covered just the introductory lecture of your torsion in a circular shaft, where I have already explained what do you mean by torsion, what do you mean by twisting moment, what do you mean by bending moment, and I have also informed you that how this torsion is basically the torque is calculated, and you know that for what will be the strength of a solid shaft as well as for the hollow shaft also. So here I have covered a lot of things, and I have also discussed what are the assumption that has to be considered for your torsion in a torsional theory for a pure circular shaft also, or you may say pure torsion for a circular shaft also. And hope you have liked the video. So please stay connected with me. Thank you.